I realize that the band kids are away, but if they sit down and watch this and come and grab the sheet, they should be okay. Maybe I'll post the sheet as well. Ready to go, Colby? All right, so some sort of cleanup, sort of reminder, refresher about some ideas about gravitational fields. It says here, the Earth pulls on the moon. We regard this as action at a distance. That's a term that you should have some understanding of. So that means that there's a force applied even though there is no contact. Action at a distance, right? It's like me using my Jedi powers to move the pen that's over there on that table. Because the Earth and Moon interact with each other even though they are not in contact. Or we can look at this in a different way. We can regard the Moon as interacting with the gravitational field of the Earth. So some scientists got together and got thinking, how can we explain, how can we validate this idea of being able to apply a force even though there's no contact? And so they came up with this idea of the gravitational field. The properties of the space surrounding any mass can be considered to be altered in such a way that another mass introduced to this region will experience a force. This alteration of space is the gravitational field. It's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the mass of the Earth and other planets or stars that are the source of these fields. The field concept plays an in-between role in our thinking about the forces between different masses. So it's a way for us to sort of explain what is going on. And if I draw a picture, here's my distant rocket ship. Maybe this is Earth. Yeah, it looks kind of like Earth, right? And it's zooming by the Earth. Well, as it goes by the Earth, it's going to be, what's going to happen to it? It's going to be attracted to the Earth, right? So if it was trying to zoom by, it would be bent by the Earth's gravitational field. And if I draw in the Earth's gravitational field, it would look like that. And I've drawn some of these for you already. Keeping in mind, what does the lines represent? How do I show a stronger gravitational field? Closer, more lines closer together. Right? And so this idea of action at distance, this spaceship it's not touching the Earth, but it's touching the gravitational field. So that's sort of their justification for how this works. Does that sort of make sense? Gravitational field is an example of a force field. Something in the space experiences a force due to the field. Another force field that you may be familiar with is a magnetic field. You've probably seen iron filings lined up in patterns around a magnet. You guys ever seen that kind of thing before? Teacher puts a magnet down, sprinkles some iron filings on a piece of paper. I don't see a lot of yeses, so I'll maybe do that for you someday. You've probably seen iron filings lined up in patterns around a magnet. The pattern of the filing shows the strength and the direction of the magnetic field at different points in the space around the magnet. Where the filings are closest together, the field is strongest. Notice here, in this picture here, let me make this a bit bigger. Do you guys have this picture? You guys don't have that picture? Where are the lines closest together? Right here. You see, like it almost looks like there. It's almost looks like it's hair. Right there. Right around the, what are those called? Of a magnet. The N and the S. What are those called? The poles. Right around the poles is where the magnetic field is strongest. Would the same thing be true for the Earth and our poles? Is gravity the strongest near the poles? Or is gravity uniform throughout the Earth? It's a little bit different. It is not like that. There's no extra gravity at the poles. Okay? The Earth's magnetic field is something different. Where the filings are closer together, the field is strongest. The direction of the filing shows the direction of the field at each point. Okay, so the pattern of the Earth's gravitational field can be represented by field lines, like I've shown you already. Like the iron filings around a magnet, the field lines are closer together where the gravitational field is stronger. That's important. Field lines are closer together where the gravitational field is stronger. At each point on a field line, the direction of the field at that point is along the line. Arrows show the field direction. Gentlemen. Okay? And gravitational field is always which way? Towards the center. Gravity is always down. A particle, astronaut, spaceship, or any mass in the vicinity of the Earth will be accelerated in the direction of the field line at that location. The strength of the Earth's gravitational field, like the strength of its force on objects, follows the inverse square law. Now, have we talked about inverse square laws before yet? No? Not never? Really? Okay, well then we better do that. It is strongest near the Earth's surface and weakens with increasing distance from the Earth. Let me just get rid of some stuff here. Okay, so inverse square law means this. If you are 2 times as far away from the Earth as you are, that's actually the center, like if it's 9.8 here on the surface of the Earth, if you went 2 times farther away, what would be the strength of the Earth's gravitational field? Well, it wouldn't be 1/2. As you get farther away, it gets less. It would actually be 1/4. What's going on here? If you're 3 times as far, it's going to be what strength? 1/9. Where am I coming up with these numbers? It's the inverse square law. So you go 1 over 2 times. 1 over 2 squared is equal to 1 over 4. 1 over 3 squared is 1/9. So if you are 4 times as far away, 1 over 4 squared. 1 what? 16th, and so on. That's what the inverse square law means. Inverse means you flip it upside down, and square simply means that you square it. Okay, challenge question. Tough question. What if it's not an integer number? What if it's not 2, 3, or 4? What if it's something like 1.5 times 1.5x, 1.5 times the distance? How do you do that? Well, you go 1 over 1.5 squared. And what is 1 over 1.5 squared? What's 1.5 squared? 2.25. So could we just write that as 1 over 2.25? Can we just write it like that? Yes, let's do that. Got that, Colby? Yeah. Put the phone down, man. Pay attention. You'll be absolutely amazed what you might learn. Okay, so here's the exciting part. The gravitational field of the Earth exists inside the Earth as well as outside. If you dig a hole, there's still gravity, right? Does it matter how big that hole is? Anybody ever been to the Grand Canyon? Nobody? Yeah? Is there gravity at the bottom of the Grand Canyon? Of course there is. Right? The bigger the hole doesn't mean that it's gravity-free. To investigate the field beneath the surface, imagine a hole drilled completely through the Earth, say from the North Pole to the South Pole. Jason, grab my globe for me, would you? So we're going to dig a hole all the way from the North Pole to the South Pole. Forget about such impracticalities such as lava and high temperatures, and consider the kind of motion you would undergo if you fell into such a hole. Thank you. Okay, so if we were to dig a hole, does it have to be from pole to pole? It's going to be like from right here in Dauphin to, where would you end up? Where would you end up? China? Everyone always says China, right? Is it China? No, you wouldn't end up Monterey. Here's Dauphin right about there. Where would you end up? In fact, because the Earth's surface is covered by 70% water, you've got a 70% chance that if you start digging a hole, you're going to end up with water. Not near as much fun. If you were going to actually end up in China, you would have to have been digging from somewhere like in South America, like Argentina or someplace. Yeah, I don't know where that sort of myth about ending up in China. You see that in the old cartoons. Okay, so if we were to dig a hole and then jump in, what would happen? If I were to dig a hole and then jump in, I would fall. Would I speed up as I'm falling? All the way, Jason? All the way to the other end?
Only until you get to the center.
Only until I get to the center, and then what? I would stop right there at the center and sort of like just kind of hang out, hover?
Yeah.
How would I slow down?
Because the ground is pushing under all the.
Oh, So you're saying that because I'm like halfway down the hole, there's earth above me that it would be pulling me up. Can't fall upwards. Well, upwards is kind of a funny thing. Like, what is upwards? Like, what's wrong with having the globe like that? Who says we're on top? It's just our Eurocentric view of the world, that's all. Okay, so let's talk about the trend here. He's saying you can't fall. What would happen? Jason says you would hover at the center, although I think he's questioning now maybe whether that's right or not.
Well, like, you wouldn't fall all the way back.
You wouldn't fall all the way?
You wouldn't go to the other side.
You wouldn't go to the other side?
Unless you had great enough velocity. Like, you'd have to be, I'm sure you'd have to be propelled fast enough all the way to get to the other side.
Okay, well, let's read here and see what happens.
Once you get...
Stop worrying about that. How long do you think that trip would take if you were to fall all the way through COVID? A week.
Yeah, well, it depends how fast you go.
Well, of course. It's kind of part of the question. You think it would only be a week?
36.
36 minutes. It's pretty specific. Forget about impracticalities such as lava and high temperatures and consider the kind of motion you would undergo if you fell into such a hole. If you started at the North Pole end, you would fall and gain speed all the way down to the center and then overshoot and lose speed all the way up to the South Pole. So you would jump in and you go faster, 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 faster. You'd get to the center and then you would start going, you'd be going really fast. You'd start going slower and slower and slower and slower, and then you would eventually pop up, let's say you ended up in the Antarctic. If there was a penguin walking around in the Antarctic and you had your hole dug all the way, and Colby jumps in and he pops out in the Antarctic, what would the penguin see? He would see Colby popping up into the ground, but he would be feet first, upside down. He would just kind of pop out of the ground right there, wave his toes, and then what would happen? Fall right back down. All the way, and then we'd be here and often, and then Colby would pop up, and then he would be head first. He'd be right side up, if you will. That's exactly what would happen. Now, this is all assuming what? Would you have enough velocity? You have to assume that the Earth is a perfectly round sphere, and it's not. Actually, it's kind of squish a bit like this. You ever take a water balloon and spin it? Well, like this, probably not. Who does that? Right? I'm trying to think of something else. It spins like this, right? When you spin something like this, what happens is the inertia actually causes the outside to sort of stretch this. So the Earth is actually sort of scrunched, like if I squeeze it together, so it's not perfectly smooth and sphere. So, yeah, if Colby tried that, he probably wouldn't end up popping up and show the thing. And even if it was a perfect sphere, we were talking about altitude as well, right? Like we are a certain distance above ground level or sea level here. It might be a different altitude down there. So there's a lot of factors. And there's lava in the middle, all that stuff, right? Anyways, so you would gain speed toward the center, lose speed moving away from the center. Without air drag, the one-way trip would take nearly 45 minutes. Only 45 minutes, not a week. 36 is pretty close. 45 minutes to go from there to there. That's assuming that there's no wind resistance. Now, obviously, there would be. If you failed to grab the edge, you would fall back toward the center, overshoot, and return to the North Pole in the same time. It'd be about a 90-minute trip there and back, if you could do it. Repeat this with an accelerometer of some kind. So what is an accelerometer? You guys know? It's a thing that measures acceleration. Your acceleration at the beginning of the fall is g 9.8, but you'd find it progressively less as you continue toward the center of the Earth. How come? How come? I've shown you that picture, right? I've shown you this picture that says, where's the gravity strongest? Where the lines are closer, at the surface of the Earth, they're closer. How come it doesn't continue on forever? Like, how come it's not strongest right in the middle? Because it's not. Any ideas? Because as you're being pulled downward toward the Earth's center, you're also being pulled upward by the part of the Earth that is above you. That's exactly what Jason was saying, right? You were thinking that you were going to start to slow down. You're sort of right. You would just not speed up as much. Right? Again, you're confusing velocity and acceleration. So you would fall, continue to fall, faster and faster and faster, you just wouldn't be speeding up as fast. Okay? Because there is Earth above you, pulling you up as well. In fact, when you get to the center of the Earth, the pull down is balanced by the pull up. You are pulled in every direction equally, so the net force on you is zero. Interestingly enough, there is no acceleration as you whiz by with maximum speed past the center of the Earth. The gravitational field of the Earth at its center is zero. There is no gravity at Earth's core. How come? Because you've got all this mass all around you, above you, below you, to your left, to your right, to your front, to your back. Feels like a hokey pokey here. After all, that is what it's all about. So the song goes. The acceleration at the center of the Earth is zero. How come you don't float? Because you're already moving. You're already moving. Now, Jason, if we were able to dig a hole and attach a ladder and walk our way down to the center of the Earth, and then jump off, what would happen? Would you fall down? Would you fall up? Or would you hover? The answer is you'd hover. How come? Because the acceleration of the Earth, the gravitational field at the center of the Earth is zero. But you have to get there without moving. Like you have to be not moving when you jump off the ladder. The strength of the gravitational field at any point is measured by the force on a unit mass there. If a force F is exerted on a mass m, the field strength is F over m, and its units are newtons per kilogram. We've talked about that. Gravitational field strength. Newtons per kilogram. Now, interestingly enough, you would gain acceleration during the first few kilometers beneath the Earth's surface. You would actually fall in, you'd actually speed up. It would be more than 9.8. Because the density of surface material is much less than the condensed center. The mass of the Earth above you exerts a small backward pull compared to the disproportionately greater pull of the denser core material. This means you'd weigh slightly more for the first few kilometers beneath the Earth's surface. Further in, your weight would decrease and would diminish to zero at the Earth's center. Now, we're not going to do that, obviously. Can you imagine the paperwork that I need to dig a hole and go to the center of the Earth? All the risk assessment I have to do. Usually I click on this thing. It hasn't worked in a number of years. I'm guessing it's not. You can dig and find out where you end up on the other side of the Earth. But it hasn't worked in a long time. See, like I'm supposed to start digging here. Your hole ends here. Really? No, it doesn't. If I dig there.
You're dumb.
Hey?
You're dumb.
See, it hasn't worked for a long time. Oh, this one might be new, though. No map. It's almost easier just to look at it globe. Okay, so, do you have these questions somewhere? I think you do, right? Are they in that box? The black box at the bottom there? I think they are. Okay, so you should know these. It says clickers. I'm not going to bother for two. If you stepped into a hole through the center of the Earth and made no attempt to grab the edges at either end, what kind of motion would you experience? Would you fall all the way through at a constant speed and stop when you reach the other side? Would you fall all the way through, speeding up the entire time and stop when you reach the other side? Would you oscillate back and forth? To oscillate means to go back and forth. With a changing speed, simple harmonic motion, or would you oscillate back and forth with a constant speed, simple kinematics motion? Is it A, B, C, or D? Who says A? Fall all the way through at a constant speed, stop and reach the other side. Anyone say A? No one says A. B, fall all the way through, speeding up the entire time and stop and reach the other side. B, anyone? No B's. Would you oscillate back and forth with a changing speed, simple harmonic motion? Anyone say C? When in doubt, go with C, apparently. What about D, oscillate back and forth with a constant speed? Anyone? Well done, you guys. It is C. It's a changing speed. It's called simple harmonic motion. Here's the fine print right here. You would oscillate back and forth in what is called simple harmonic motion. Each round trip would take nearly 90 minutes. Interestingly enough, we'll see in the next chapter that an Earth satellite in close orbit about the Earth also takes the same 90 minutes. All those satellites that are up there for GPS take the same 90 minutes to go all the way around as falling right through. How come? What's causing them to orbit? Gravity. It's exactly the same process. The only difference is, instead of falling all the way through and accelerating, it's doing what? Falling around. It's going sideways, but still falling. It's exactly the same concept. Okay? Halfway to the center of the Earth. Halfway to the center of the Earth. So we're talking like halfway. There's center. So halfway to the center, right there. Would you weigh more or less than you weigh at the surface? Would you weigh more or less at the surface? How many people say A, way more? Nobody. How many people say way less? B? Several. How many people say C, weigh the same? A couple of brave people, 3 brave people. The answer is D, you would weigh less. How come? As you go down, the gravitational field strength actually decreases because there's Earth above you pulling you up. Here's the fine print. You would weigh less because the part of the Earth's mass that pulls you down is counterbalanced by the mass above you that pulls you up. If the Earth were of uniform density, halfway to the center, your weight would be exactly half your surface weight. Since the Earth's core is so dense, about 7 times, you would be somewhat more than half surface weight. Exactly how much depends on the Earth's density, varies with depths, information that we don't really know right now. So, anyways. What do we got left here? Oh yes, weightlessness. Okay, we've talked through this already, but let's just go do it again. I know I got a video at the end of this to show you. This is sort of a review, I guess. Force of gravity, like any force, causes acceleration. Objects under the influence of gravity accelerate toward each other. We're almost always in contact with the Earth. For this reason, we think of gravity primarily as something that presses us against the Earth rather than as something that accelerates us. This pressing against the Earth is the sensation we interpret as weight. Stand on a bathroom scale that is supported on a stationary floor. The gravitational force between you and the Earth pulls you against the supporting floor and scale. By Newton's third law, the floor and scale in turn push upward on you. Located in between you and the supporting floor are springs inside the bathroom scale. The springs are compressed by this pair of forces. The weight reading on the scale is linked to the amount of compression of the springs. Now, if you repeat this weighing procedure in a moving elevator, you'll find your weight reading would vary, not during steady motion or constant speed, but during accelerated motion. If the elevator accelerates upward, the bathroom scale and floor push harder against your feet, and the springs inside the scale are compressed even more. So you have a greater weight here when you are accelerating up. You can see that by the cartoon clouds. Right? If you slow down as you get to the top, you have less weight because you're slowing down. And then, of course, if the cable breaks, and no one wants that to ever to happen, you would have no weight. Well, for a moment or two, it would be exciting, wouldn't it? Does that happen very often, do you think, that the cables break in elevators?
Yeah.
Unlikely, right? Do you think there's just one cable? You think so? There's just a guy, like, yeah? Giving her. Oh, yeah. I think we can get all that. Now, what about this? If you define weight as gravitational force acting on an object, then you still have weight whether or not you are freely falling. Astronauts in Earth orbit who float freely inside their capsules are still being pulled by gravity and therefore have weight. But you in the falling elevator and the astronauts in the falling satellites don't feel the usual effects of weight. Did we show the TED Talk about the effects of gravity in space? I think we watched that, didn't we? Wasn't that you guys? I think we did. You feel weightless. That is, your insides are no longer supported by your legs and pelvic region. Your organs respond as though gravity were absent. You are in a state of what we call apparent weightlessness. You feel weightless. You are not actually. To be truly weightless, where would you have to be? You'd have to be away from everything. You'd have to be far out in space, well away from the Earth and other attracting stars and planets where gravitational forces are negligible. In this truly weightless condition, you would drift in a straight line path rather than the curved path of an orbit. In a more practical sense, we define the weight of an object as the force it exerts against a supporting floor or weighing scales. According to this definition, you are as heavy as you feel. The condition of weightlessness then is not the absence of gravity, but the absence of a support force, something holding you up. That queasy feeling you get when you're in a car that seems to leave the road momentarily, when it goes over a hump or worse off a cliff, is not the absence of gravity. It is the absence of a support force. Astronauts in orbit are without a support force and are in a sustained state of weightlessness. That causes space sickness until they get used to it. Interestingly enough, your food tastes different when you eat in space.